First, we import the Python math module. Then we import PyTorch. We print the PyTorch version we are using. We are using PyTorch 0.3.1 post 2. Now, let's manually create the PyTorch tensor we're going to use in this example. We use torch.float tensor. We pass in the data structure and we assign it to the Python variable pt tensor x. We construct this tensor in this way so that it will be straightforward to calculate the bias standard deviation of the tensor. Then we print the pt tensor x Python variable to see what we have. We see that we have one tensor that's sized 2 by 3 by 3, and it's a PyTorch float tensor. First matrix is full of 36s, second matrix is full of 72s, just like we defined it. Next, let's calculate the bias standard deviation of all the elements in the PyTorch tensor by using the pytorch.std. We're passing in our pt tensor x Python variable, and we're going to set the parameter unbiased as false. That means we're going to be calculating the bias standard deviation, and we're assigning that value that's going to be returned to the Python variable pt biased stdx. Then we print this variable to see the value. We see that we get 18.0. Alright, now that we have a result, let's double check it manually to make sure we're comfortable with what was calculated. First, let's reacquaint ourselves with how we calculate the bias standard deviation. First, we calculate the mean, then we subtract the mean from each element, then we square the result, and we do a summation over all of the elements, and then we divide the summation result by n. Then we take the square root. If we were doing the unbiased estimator, then this would be n minus 1, which is Bezel's correction, but because we're calculating the bias standard deviation, or the population standard deviation, we divide by n. When we calculate the bias standard deviation, we are asserting that we are calculating the standard deviation over the whole population, which is why we use n rather than n minus 1. So now let's check the calculation manually. We'll start by calculating the mean of the tensor using pytorch.mean and passing our pt tensor x variable and assigning the result to the Python variable pt tensor mean x. We then print the pt tensor mean x Python variable to see that the value is 54.0. Now that we have the mean in hand, we want to subtract the mean from every single element in our pt tensor x PyTorch tensor to demean it. Then we're going to assign it to the Python variable pt tensor transformed x. When we print this variable, we see that the first matrix is full of negative 18s, the second matrix is full of positive 18s. 36 minus 54 is negative 18. 72 minus 54 is 18. Okay, we're happy with that. That makes sense. Then we want to square each element using PyTorch's POW operation. So we pass in our pt tensor transformed x, and we're going to raise it to the power of 2, and we assign it to the Python variable pt tensor squared transformed x. We can then print this variable to see what we get. We know that 18 squared is 324, and negative 18 squared is 324. So this makes sense. Now that each number has been demeaned and squared, let's sum all of the elements in the tensor to get one value. So we use pytorch.sum. We pass in our pt tensor squared transformed x variable, and we're going to assign it to the Python variable pt tensor squared transformed sum x. When we print this variable, we can see that we get the value 5,832. Because we are using a tensor that is 2 by 3 by 3, it means there are 2 times 3, 6, times 3, 18 elements. Also remembering that we're doing the population standard deviation, or the bias standard deviation, we don't have to use Bezel's correction, so we're going to divide this number by 18 and not 18 minus 1. So we do 5,832 divided by 18 to get 324.0. Lastly, we use the Python math module's square root to take this expression and get the square root of it, and when we do that we get 18.0. Let's compare it to the bias standard deviation calculation result we computed earlier. So we print pt biased stdx, and we see that it's 18.0 as well. Perfect. We were able to calculate the bias standard deviation of all elements in a PyTorch tensor by using the PyTorch Tensor std operation.